Hi, my name is Abby. I am a current SWE at TileDB. Formerly, prior to TileDB, I was at CMU, Carnegie Mellon. I was doing a master's degree with a research thesis component, and I was working with Professor Andy Pablo, who you may all know. And this presentation consists of the work that I did with Andy. I researched extensibility in general, but this presentation will mostly center on Postgres since this is a Postgres conference. And my main goal with this presentation is to provide a researcher's perspective on database extensibility within the Postgres ecosystem. Oh yeah, also notably, this title slide is Andy's idea, not mine. But it has a giant barrel that says database of death, and it's supposed to be a looming imagery for the Wild West we're about to unfold. Yeah, and my collaborators, other ones, are Professor Dave Anderson and Marco Slot, who you may know for Citus and Crunchy Data. So to start, we'll go over the basics. What is extensibility? So we'll go over both that and a brief history. So let's review what extensibility is. Extensibility is the capability of the database system to let custom software extend its capabilities. And an extension is an instance of this software. So Postgres supports many, many, many types of extensions, and so do many other database systems. All right. So for the next thing we'll cover is a very brief history of database system extensibility. One of the first instances of extensibility is in the 1970s with Ingress, which is Postgres' predecessor. And Ingress first supported both UDTs and UDFs. Following Ingress, there was an extensibility boom in the 80s and 90s. So this includes Starburst, which is extendable query processing, Exodus, which is a framework for database extensibility that includes a lot of helpful, supportive libraries to help databases develop extensions, but does not provide a framework itself. So these include kernel modules, a storage manager, and a rule-based query optimizer so that people can easily extend their query processing modules. And the last of these is Genesis, which on the complete other end is the opposite of Exodus. It provides simply an interface. Developers fill in functions for these interfaces, and then you combine these modules to form extensions. So this is a little bit similar to the whole composability movement that's going on pretty recently. The Velox people had a VLDB paper that kind of covered this. Anyways, after 1980s, extensibility in the research sphere kind of died for a bit until we reach now, which is within Postgres, the modern era of extensibility. So this is a bit haphazard, right? Because I suppose Postgres always supported configuration parameter hooks for a little while, but in 2007 is kind of when things started to get pretty serious, right? The planner hook was added in order to support auto-explain, which came out a couple years later. And the planner hook essentially allows any extension to override the planner. In 2008, extension hooks were added. So these are hooks that allow you to override significant parts of the executor. And in 2011, the create extension command was supported, which essentially allows extension developers to package multiple types of extensibility, such as UDFs or indexes or UDTs. They can shove them all into one package. And this is kind of the modern extensibility module we have in Postgres today. And as a result, extensions development skyrocketed. Now there's a ton of people that work in the Postgres extension space. So it leads us to where we are now. Many, many companies, including the companies that sponsored this conference and the companies where many of the attendees of this conference work, are doing really impactful stuff in extensibility. Additionally, the big cloud providers, the big three, Google Cloud, AWS, and Azure, recognizes the importance of extensions. All of these platforms support many, many Postgres extensions in their managed Postgres instances. And lastly, I think it's important to recognize Postgres's specific impact on the extensibility scene compared to other databases. Postgres just has so many more third-party extensions compared to essentially any other database system. And part of this presentation is actually going over why this is the case. But yeah, even if all the other databases on this list are also widely used and have a large community, Postgres is the only one that really has a huge extensions community. Okay, so now that I've uncovered all of these really nice positive things about Postgres's extensibility environment and just the fact that it's very popular, let's see what happens when we try adding more than one extension for a Postgres instance. So for this example, we'll combine Citus, which is distributed Postgres, as an extension, along with AutoExplain, which is one of the classic Postgres extensions for execution logging. And yeah, we'll see what happens. And this resulted in a bug 3 weeks ago, actually, which is really funny, but this is pretty standard, right? Basically, some cache lookup failed, and so this doesn't work. And so, as a researcher, I was fascinated because these are two very well-known extensions. And this is so far down the Postgres development sphere, and they still break each other, And it kind of raised lots and lots of research questions that could be pursued, right? Especially since we kind of view Postgres as the, one of the most well-designed extensibility frameworks out there. So the first question really is what design decisions of Postgres's extensibility, or in particular database extensibility, caused this conflict and similar? In general, how well designed is database extensibility, both inside and outside of Postgres? And really, the end goal is, can we design extensibility to not have these conflicts, right? And what can we do, even on a practical scale, to improve the extensibility of existing database systems? Alrighty, so now that motivation is covered and my research questions have been addressed, we move on to the first part of my research, which is an academic survey on Postgres. So really, the first step of any researcher, writing a thesis, is that you just read related work, both from the internet, you read lots of docs, and you read research papers, right? And one thing that I noticed is that lots and lots of database systems, for instance, Postgres, MySQL, and SQLite, have very well-defined and established types of extensibility support. But there are no research papers on the classification of extensibility design. There's no larger academic understanding of what database extensibility is. So the first part of my research focuses on better organizing and classifying these types of extensibility support. And this would be in order to kind of really understand the database extensibility sphere, and in particular, what design decisions do database developers have to make when designing an extensibility framework. And so this leads to the first part of my research. I created a taxonomy on database extensibility and categorized existing systems using the taxonomy. So the survey method is essentially, it's quite simple, actually. Reading database systems, reading code, reading extensions, sometimes reading mailing lists. And so I want to highlight a few things about this survey method. For one, many other database systems that are popular and well used, for instance, Oracle, SQL Server, even the big cloud data analytics systems like Snowflake and Databricks, support UDTs and UDFs. However, there's two things that differentiate the list of databases that I've surveyed, so Postgres, MySQL, SQLite, DuckDB, and Redis, compared to these other ones. One, they're closed source. So these databases are open source, and other ones are closed source. Closed source makes it really difficult to study extensibility in general, just because of it's, you can't even read the implementation. And the other thing is that I tried to pick extensibility systems to study that were, they had more comprehensive support of extensibility. So they weren't, only supporting UDTs and UDFs. Yeah. And so for the sake of this presentation, I'll focus on Postgres. But feel free to ask me about other findings, either in questions or after this presentation. So the first of these findings, the survey findings, was the types of extensibility that I discovered. This diagram is essentially based on common parts of the DBMS that most relational database systems share. I do recognize that Postgres supports many different types of extensions outside this diagram. For instance, GUC hooks or text search dictionaries. And in the next slides, we'll quickly go over each of the DBMS extensibility types, right? So the first two types are UDTs, which are like physical types with binary encoding and support functions like comparators, and UDFs, which are custom functions either in other languages or in the source code language, which is C for Postgres. And these are things that most people, I think, should be familiar with. The next type of extensibility is external tables. External tables are essentially akin to Postgres' foreign data wrappers, but the research classification of them would be that they are methods of viewing outside data within an internal data representation. So essentially, how these are implemented is that you fill in a function API to treat outside data, like cloud files or different file formats like Parquet, as internal DBMS data. The next kind of extension is index access methods. So these provide additional index implementations. One quick fun fact about these is that these are really nice for UDTs. UDTs will often combine both index access types and a UDT that is optimized for the index, or the index is optimized for the UDT. So pgvector also includes HNSW support, for instance. And the fifth type of extensibility is catalog modifications. So while indirect catalog, these are extensions that modify or access database metadata, indirect catalog modifications are actually done by many extensions. For instance, DuckDB's catalog extensions function as a wrapper around another DBMS's catalog. So these are essentially external tables, like their Postgres scanner is you can load a Postgres table as a DuckDB table, but the way they implement it is that they override the catalog extension interface, and all their catalog functions will point to the Postgres catalog, which is really interesting. So these types of extensions are not necessarily always cut and dry, but they are also similar to, there's different categorizations per DBMS. Okay, so the next types of extensions, this slide is mainly focused on ones that are location specific. So client authentication extensions modify client authentication logic. So this would include stuff like password validators or query rewrite plugins. Parser extensions modify parser logic. So this is adding new syntax. Query processing extensions modify the query execution layer. So this is the planner, optimizer, executor. Postgres has a lot of these, which is very rare. Utility commands modify all commands that aren't really insert, select, update, or delete. And so these are DDL commands. And storage manager extensions, they modify the storage manager layer. But notably, Postgres' support of these is pretty limited compared to MySQL. MySQL storage engines are a well-known example of storage manager extensibility. So within each DBMS, these are the types of extensibility supported. And as we can see, Postgres supports the most types of extensibility, with 9 out of 10 being supported. And the only type of extensibility Postgres really doesn't support is parser extensibility. And honestly, despite the clear difference in extension ecosystem, DuckDB, MySQL, and MariaDB don't support significantly less types of extensibility. They still support quite a lot of extensibility. Part of this is just because DuckDB is pretty new. they've been very recently adding extensions to their database. And MySQL and MariaDB mainly support lots of storage engines, but don't have a particularly active environment in other types of extensibility, despite supporting them. So the next categorization addressed in my survey was the interface design decisions in the DBMS when supporting extensibility. So the first of these is whether a database system chooses to extend or override its host functionality. When it extends functionality, that means an extension adds new features without changing the system's existing functionality. So this would include UDFs and UDTs. While overriding is when an extension replaces parts of its host DBMS code, for instance, like utilizing a hook in Postgres. So Postgres supports both. Additionally, the next decision they have to make is considering state modification. So this is like whether a DBMS can modify database state, system state, or extension state. The database state is essentially user data. So this includes table data, index data, materialized views, the catalog. System state, we refer to as the internal DBMS data structures. For instance, like arguments in a hook that you pass from one thing to the one function and then you modify. And extension state is, does the DBMS allow extensions to keep its own state or own metadata? And Postgres allows extensions to modify all three of these things. Okay, the next design decision is protection. Protection really asks two questions. First, are extensions isolated from each other? Are there specific mechanisms to keep extensions from modifying the output of other extensions? And second, can attackers utilize extensions to attack the database system? So the answer to this is kind of. Postgres definitely has very limited extension isolation in the sense that extensions call each other's hooks within its implementation. And this makes it kind of like, essentially an extension can explicitly deride another extension's execution. But the security part is a more complicated question. It opens a whole other can of worms. But it is notable that Postgres does not allow users to install extensions with super user permission. There's like a certain privilege level to be able to install extensions. And the super user extensions modify the file system. They modify internal data structures, and that's why they cannot be installed by a regular user of Postgres. The next categorization that we covered is determining the components that extensions use to build extensions. These are really a subset of the ones that Postgres provides, but these are also ones that can be generalized to other database systems. So the first of these are background workers. Background workers are essentially spun up threads or processes that help extensions execute what they need to do. For instance, like pgcron is a pretty well-known extension that uses background workers in the sense that they just spin up background workers to do extra jobs. The second of these is memory allocation mechanisms. So this is like a special type of malloc specifically for extensions. It is notable that these first two are very process-based, like process model-based. Postgres has a process-oriented process model, so every time they execute a new query, a process is spun up instead of a thread. A lot of database systems are thread-based process models, so this would allow the native language constructs like pthreads and malloc to be usable as both background workers and memory allocation mechanisms. But because Postgres is a process-based process model, they have a custom background worker interface, and they also have a custom memory allocation, like shared distributed memory interface. The third of these is configuration options, essentially allowing users to create their own configuration options within extensions. And the fourth of these is within Postgres, this would be modifying Postgres conf or pghva conf or GUC variables. The last of these is custom extension locking, so concurrency control. Can extensions add their own locks that are, they have their names and are used within their application? And Postgres supports all four of these system components. Lastly, when considering next extensibility implementation, you must consider its developer tools, right? So the first of these is the build infrastructure. Tools extensions use to build their extensions. So within Postgres, a few examples would be like pgxs, which is a makefile generator for Postgres. pgtle, which is it's actually an extension, but it's an extensibility framework that users without super user permission can use to develop extensions. And pgrx, which is a Rust extensibility framework. The next is testing frameworks, so essentially how developers test their extensions. Postgres has pgregress, which is not only used for extensions, but is very commonly used within extensions as a testing framework. Additionally, pgtap is an extension that provides its own testing interface. Notably, this is not really a logo, it's just the image that I got off the pgtap website. And the last of these is extension managers, so how users find extensions and manage their installation. So this includes pgxn, which is like probably the most established extension manager. Oh, David's here. Hi. Trunk, which is Tembo's extension manager. dbdev, and pgxman, along with quite a few others. Right? We conclude our survey with a comparison of Postgres' extensibility support to other database systems. So, for instance, Postgres supports the most extensibility mechanisms out of all the database systems. It supports the most types of extensibility, it has the most support for components, and it has the most building and testing infrastructure tools. Additionally, Postgres is like by far the most flexible extensibility ecosystem that I ran into. So this graph over here is essentially a quad chart that compares the safety of extensions with the flexibility of extensions. You can see Postgres is a very, very flexible environment, but it sacrifices safety. But MySQL and DuckDB are pretty similar in terms of this flexibility versus unsafe trade-off. And on the other hand, we have safe but restrictive extensibility environments, so SQLite and Redis. A little note on Redis. Redis only supports command line command extensibility. So these are UDFs that can use Redis. So there's plenty of extensions built on top of Redis, but you cannot actually modify Redis with an extension. So for instance, they have a graph database that's built on top of Redis. And this is an extension to Redis. You can there's an API that you can use to call key value stores. Yeah. So I guess the notable things are really just, even if Postgres has a really similar design to MySQL and DuckDB, it trumps it in terms of extension ecosystem. And I think this is partially due to the fact that Postgres has extensive building and testing infrastructure support compared to these other database systems. So Postgres server takeaways. One, Postgres is a very flexible extensibility interface, which I covered early. Allows for both extending and overriding, right? And extensions can modify all state. And as a result, it kind of offers limited security and isolation for extensions. Postgres supports a variety of extensibility mechanisms. 9 out of 10 types of extensibility that we discussed in our survey. And supports all the system components. And Postgres has a robust testing and building infrastructure. And so I guess TLDR, these are, I think, largely part of the reasons that Postgres is so popular for extensions development. All right, so now we move to the second part of my research, which is the analysis portion. Right? So let's revisit Citus and Auto explained, right? With the analysis part of the presentation, we really have these two well-known, frequently used extensions that don't work when used together, right? And so we posed the following research questions based on our observations, right? How common is this problem? And if this problem is common, then why from a design perspective? Right? Given my research questions, I designed an analysis framework that has 2 different modules. The first of these modules, is compatibility testing. So essentially, compatibility testing is testing whether 2 extensions work as intended while together, whether they install successfully and they pass their unit test. This is essentially a smoke test. And when testing this, I also made sure that they tested them individually first. I don't want to like fabricate any extension conflicts, right? The second of these frameworks is modules that collect information about extensions, because I'm trying to figure out why this problem occurs from a design perspective, like extensions that have this kind of property cause more conflicts. And so we'll go over these in the next slide. And overall, the goal of this framework is truly just to understand the factors that cause this incompatibility, right? These are the framework logistics. So I ran my analysis on Postgres version 15.3. I tested it on 114 extensions, including the ones in the contrib module, the ones that are supported on AWS, Azure, and Google Cloud, a union of these. And also, extensions just have a lot of stars on GitHub, a lot of traction. They're like popular within outlets like, I don't know, Reddit or Hacker News, right? And one important component that I want to capitalize on is that I utilized pgregress for testing. So I ran all these extensions tests on pgregress. pgregress, as we know, is like somewhat flawed, and I kind of have an appendix slide on this. Another thing that I want to mention is that all the extensions are open source, and my framework does not support pgtap, but I would like to do so in the future. Alrighty, so this is a design diagram of my compatibility analysis. I keep this extension info database that contains a lot of basically all the characteristics of an extension. For instance, like this is the GitHub link and how to download it, and this is the how to run the scripts for testing. These are the arguments you pass in. I keep a JSON file per extension. And so I have an input, which is a list of extensions. Then I collect all the info from the extension database, generate the pairs of extensions to run testing on. So my compatibility analysis framework essentially takes an extensions, it generates them, and it like downloads and installs these extensions, runs the unit tests, and then it also runs pgbench, but that did not report any errors, so I've omitted it from this design diagram. And then it consolidates these compatibility results into a CSV. So it's essentially a smoke test. So this is the first set of my information analysis, right? This is essentially just taking an extension, gathering its source code, and figuring out what kind of components are present within this extension. And so we're examining these things so we can determine like whether types of extensibility utilized or hooks utilized correlates to incompatibility failure. And when I mention components, I divide extensions as supporting 7 different components: functions, types, access methods, external tables, client authentication, query processing, which includes all the planner and executor hooks, and utility commands, which is both process utility hook and logical decoding extensions. And so this is the last of my design diagrams for the source code analysis tool. Similar to the information tool, it collects the code of the extension. Then it does 2 analyses, which we will talk about in the later slides. One, it's a duplicate Postgres code analysis. And the second is a versioning code analysis. After that, I will consolidate also these results into a CSV. Yeah. So duplicate code analysis. What is that, right? Because I guess these are, one, it should be known that duplicate code analysis capitalizes on the fact that extensions copy code from core Postgres to use in their own extensions, right? And so in this diagram, we have core postgres.c, which is this file, and it contains this function called foo that's static, which means it cannot be referenced. And then extension.c just like copy paste this function because they want to use it in their extension, right? And so within qualitatively, these are either code that's copied is either static functions that they can't call, or significant portions of complicated logic, like a switch statement to set a value based on a type of node. These things are like copied over. In our analysis, we really counted only instances with more than 100 lines of tokens. I think it just makes sense to have like, you copy like 3 lines of code, and that's kind of present in many different areas of the database system. but we didn't want to like include those in our analysis. So we only counted instances with more than 100 tokens. A token is essentially an identifier, constant, special keyword, special symbol. So I guess in this core Postgres file, static is one token, void is another, foo is another, and then void is another, right? So this is like a 5-line token. Like this line would be 5 tokens. So this is about, I would say, approximately 20 lines of code. Yeah, and then I used the PMD copy-paste detector tool to help me out with this analysis. So that tool will take in 2 different code bases and determine whether there is copied code within it. CPD stands for copy-paste detector, and I will refer to this thing as CPD from the rest of this presentation. But after a decent bit of research, I still can't figure out what PMD stands for, so it'll just be PMD. I don't know what it means. Versioning code analysis capitalizes on the fact that extensions utilize versioning logic in their extensions. So versioning logic is essentially within the Postgres code base. We have this macro, like macro constant called PG version num. And PG version num essentially is the version. And it'll like, you know, if it's 14, like this number correlates to the Postgres version. And extensions utilize this kind of logic. It's like, if PG version num do this, otherwise do this, to support different logic for each version, because the versions of Postgres change so dramatically from one another, especially, like, it doesn't really change dramatically in the sense of like a user compatibility perspective, but even within minor versions, sometimes the internal data structures change or refactoring happens, and then extensions need to account for this, especially ones that utilize, you know, dig more like, or more complex, use planner or executor hooks. Yeah, so these things change. It's also notable that, one, this results in overly hard to read code because there's a bunch of different macros at points in code. And extensions actually take 2 approaches to this problem of Postgres changing versions. One, they either use this versioning logic, or 2, they just have many, many different versions of their extensions. They have a bunch of releases that correlate to different Postgres versions. So now we'll go over the results of my slides. OK, we're a bit short on time, but I think that's OK, right? Before I present the results of my research, I think I need to discuss the metrics I choose to collect. And I'm dividing the choice of my metrics into the questions I choose to research. So first, the question of how common is this incompatibility problem? I'll keep track of how often tests failed in general and per extension. And you know, I'll keep track of this main metric. It's the number of pairs of tests failed versus the number of pairs where an extension is included, which is equivalent to the extension failure rate. So for instance, take this small example. I ran tests on 3 extensions, A, B, and C. Like, you take 3 extensions, you permute them, and then all the pairs with A are going to be AB, AC, BA, and CA. Let's say only one of these pairs fails, so CA fails. Therefore, the extension failure rate is 1/4 or 25%. I guess more qualitatively, it's an extension niceness score. So next of these metrics is what factors contribute to higher incompatibility rates. So for instance, I keep track of the components utilized, right? Whether an extension utilizes EG-query processing, and that results in higher compatibility failure rates. I also include metrics on extensions copying source code, like the percentage of extensions that do it, and if so, what percentage of their code is encapsulated within it. And metrics on extensions utilizing versioning. So how many extensions utilize versioning? If so, what percentage of their code is encapsulated within versioning statements? So this is the result of my compatibility analysis. Out of all the pairs of extensions I ran, so yeah, 17% of them failed. And really, our first question is whether extension compatibility is a common problem. And so notably, I record extension pair failures, not specific test failures. And takeaway, extension compatibility is a common problem, right? 17% is a lot. But that's not a particularly nuanced take, so the next view of our compatibility analysis seeks to add more nuance to our understanding. And so this is a histogram of the extension failure rates. As we can see, most of these are actually most extensions are pretty nice or tame. They fall within the 0% to 10% failure rate, right? And this rate is actually inflated by the ones that in the tail that fail a lot of different extensions, right? Takeaway, most extensions don't produce conflicts, but some produce a lot of compatibility conflicts, right? And so I guess to put this into practice, I've included a little slide of little fun messages or fun reasons that extensions failed, right? For one, LSM3 fails because it deadlocks with a bunch of other extensions on this particular statement, which is a background worker bug in LSM. PGBigM, which is a bigram index, fails because its operator classes result in an error in the Postgres GIN validator, because the GIN validator kind of just thinks that this operating class is part of them, like their thing, but it's not. PL Profiler loaded before PGStat statements has a bug as fixed as of 15.4 in their shared memory startup hook. So essentially some lock is not registered and the database shuts down, but when you load them reversely, it works. And a really funny one, PG Audit tests fail with password check because PG Audit doesn't use a good enough password in their tests. Okay, so this marks the beginning of the analysis of our information analysis, which is like a partial measure of extension complexity, right? So as you can see, most extensions don't really use that many components, right? In fact, 86% of extensions, or 87, I guess, incorporate UDFs. So if we take that data and shove it in, think about it with this data, it really means that most extensions are just UDFs, right? But there's still a lot of extensions on the tail end. Citus utilizes the most number of components at 6. Timescale's right behind it with 5, which is, expected. Yeah. And so takeaways, most extensions utilize a small number of components. The next set of metrics is with regards to copied Postgres code. We found that 19% of extensions copy Postgres code. And the takeaway is extensions copying Postgres code is really a common phenomenon. Next, for each extension that copied the code, which is 22 of them, we kept track of the percentage of extension C code base consisted of copied code. And, as previously, this extension is long-tailed. Most extensions do not use that much copied code, but some of them really use a lot of them. And so the histogram consists of extensions with greater than 0% copied code. The max is page inspect, which copies 75.5% of its code. And so the takeaway really is most extension code bases do not have a lot of copied code, but there's a long tail. Okay, so for versioning code logic, 45% of extensions utilize versioning logic, which really, to review, is just when they case on different versions with PG version them. And really, takeaway, extensions using versioning logic is a very common phenomenon, right? That's a lot of extensions. The next view of our versioning data is a histogram, which records the percentage of the code base encapsulated in versioning macros, right? And so the max is the maximum of code, percentage of code encapsulated is HypoPG with 23.85%. And really, the takeaway is most extensions don't use versioning logic often. But I guess more generally, how I interpreted this data is that the standard extension, most standard extensions, is an extension that has mostly UDFs, maybe a UDT, doesn't utilize hooks, or many components, or versioning, and is relatively tame. But there are definitely a few very comprehensive extensions that utilize many components of Postgres' extensibility support, and therefore have lots of copied code and lots of versioning, and they really get into the weeds of Postgres in their extension. So after we've collected all this data, we ask our second question. What is the relationship between compatibility failure rates and extension properties? So, now that we have all the data, we can figure out whether there are properties that connect each extension's compatibility rate with all the extension's characteristics collected. These characteristics include general measures of code complexity, such as more lines of code or more components utilized. They also include all the hooks that I kept track of, and all the types of components, like individually, and also whether extensions use versioning logic and the percentage of code encapsulated within bounds, like does an extension have more than 15% of their code encapsulated in versioning statements, e.g., and whether extensions copy core Postgres code and how much. Overall, we found 4 properties that resulted in a higher incompatibility failure rate. So for people that are aware of stats, this is a p-value below 0.1, but really no need to understand that, and this is on a t-paired test. So first, the number of types of extensibility utilized, and whether an extension had more than 500 or 750 lines of source code. These are just general measures of extension complexity. The third of these is the utilization of versioning logic. So it was really I think the p-value was less than 0.01, which really indicates a large difference in the compatibility measures. While partially this is due to complexity, I also think that the versioning logic makes code more unreadable and therefore more unmaintainable. Lastly, utilizing process utility hook decreases the compatibility rate by a whole bunch. Process utility hook, for those who don't know, is a hook that overrides DDL commands, such as create or drop or alter. It's a powerful sledgehammer hook that controls a bunch of different commands and is located before the executor and after the planner, which is pretty prime location. It has many, many use cases. So these I think are the reasons that they fail, but I'm open to discussion if somebody has other reasons that they think this may be the case. And so I wanted to end this presentation with a discussion on what analyzing Postgres taught me about general DBMS extensibility design, and also some potential suggestions for improving the Postgres extensibility ecosystem after researching it for about a year. Yeah. So Postgres is really a double-edged sword, right? Because Postgres' extensibility system, as stated in my title slide, is just anarchy. You can just do anything you want, which is glorious, but also, kind of terrible at the same time. For one, it's notable that other DBMSs also support extensibility, but they don't have the extensibility ecosystem that Postgres has. Yeah. So they have, very flexible interface. This is covered in the survey takeaways, lots of internal support, and internal building and testing infrastructures that make extensibility development easier. But however, Postgres has lots of safety and maintenance concerns as well. We saw that there's really no guarantees that Postgres extensions work with each other in any case. We saw that 70% of compatibility pairs failed tests, even with a simple smoke test when they worked individually. And versioning logic is, very dicey at points. Honestly, coding extensions is just very hard in general. The code is hard to understand. People often have to resort to deeply understanding Postgres internals in order to be successful in coding complex extensions. Alrighty, so we'll conclude this with a couple suggestions. The first, I think, is that Postgres could use an extension manager. One thing that my research taught me about Postgres is that having an extension manager, especially within a system with a lot of extensions and where users are using more than one extension, that handles extension installation, ordering, etc., allows the DBMS to have more control over the execution control flow. When extensions have all the control flow, which is the current state of Postgres, they can impact other extensions, which definitely impacts compatibility. And Postgres as of really does not have an extension manager other than a lot of things that you just do by yourself. You shove extensions into shared preload libraries. You have to do that yourself. You're the one that calls create an extension. You're the one that installs all the dependencies. You're the one that gets the scripts running. And I am aware that a lot of the managed Postgres instances, they try to solve this problem with more seamless integration. But having an extension manager could solve a lot of problems within Postgres, including extensions are responsible for calling other extensions hooks. So hooks which are, okay, thanks. Okay, I guess we'll speed. Extensions need to be loaded in certain orders in order to work properly, as stated with the PL profiler PG stat statements conflict. This would also streamline disabling and enabling extensions, versus if you want to disable an extension, you have to reload Postgres, especially one that uses shared preload libraries. And it could also match extension installations to versions. This was covered somewhat in my presentation, but Postgres versions changed dramatically, extension versions changed dramatically as a result, and this could increase the compatibility between versions. The second suggestion is incorporating some semblance of my tool to the Postgres source tree. I will note that the tool is very academic code, not production ready, lots of quirks, terrible commit messages. Half my commit messages are either stuff or whip. My collaborator, Marco Slot, who worked in industry for a whole bunch of time, has very concise and wonderful commit messages, on the other hand. So essentially, users typically utilize more than one extension on database instances. And I think smoke tests or more rigorous tests between extension compatibility could streamline users' experience and also help extensions find their own bugs, like help developers find their own bugs in extension code. And my tools showed many different compatibility errors on established Postgres extensions. So I think having a tool like this could be useful. Okay, so thank you for listening to my presentation. Here are my takeaways. The slides will be public. The GitHub repo is now public, which I think some people were asking for. And yeah, that's my email. Thank you for listening. Yes?
In the flexibility and safety graph, you put Postgres at very flexible, but also at unsafe.
Yes.
There are safe extensions in Postgres. So
it's this is a rating not of the extensions in Postgres, but of the extensibility design that Postgres chose. Like what is possible within Postgres.
Right, but it's possible to restrict extensions to be safe and have their own sandbox things.
Wait.
Well, yeah, Perl U and Perl, for example.
Wait, some extensions it is possible, but there are ways to develop extensions in which this is not possible.
Because we're coding the extension in C, it can in theory be written.
If it's in C, but you can have extensions that are not written in C.
Oh, that's
Yeah, but that's
and those can be completely safe.
I mean, that's the goal of PGTLE, but this is what's it called? It's an evaluation of all the possible things, extensions that could be coded in Postgres, as opposed to we have this one extension that allows, actually PGTLE allows extensions to be coded safely, right? Because of they're allowing users that don't have super user permission to code extensions. But this is not a rating of oh yeah, there is an extension that makes this possible. This is a rating of, is it possible to code an extension where this is not possible, right? An extension developer. It's a rating of the extensibility design of Postgres.
Okay.
Yeah.
So I guess one question is, what tests did you run? Did you run just the extension tests, or did you run check world in Postgres, essentially with that?
I actually ran both. Okay. So I think I mentioned very briefly, I ran the extension unit test. Those are the ones that caught all the errors. But I also ran PG Bench with 2 extensions installed. But I didn't find any errors running PG Bench.
Yeah, I was talking about the Postgres regression test suite, because at least when I was working on Citus Codebase, we had a bunch of times where we would break Postgres tests. We wouldn't break any of our tests, but we would break core Postgres tests because we were taking the hook and returning things in an inappropriate way, obviously in development, not in released versions of Citus.
Okay. I did not. I will definitely consider that. Thank you for the feedback.
I think you hit the nail on the head with certain things, such as we're relying on hooks to call other hooks, and what was the other one? Anyway, my question is, do you have any ideas for how to fix that?
Oh yeah, so I was kind of thinking about this for a while, because I think part of the reason Postgres' extensibility system is so fruitful is because of the hooks. But I mean, there are somewhat solutions in other extensibility spaces, there's software validation frameworks, or there's a thing called like software engineering analysis tools can also be utilized, like different component dependencies, and trying to like instead of deleting hooks, I think having a system that could like validate extensions compatibility with one another, or like state analysis could be helpful in this sense. Also, I was considering for a point invariants, like including planner execution invariants, like don't modify the data structure in this way, I guess. But like I think those are the two things I have on the top of my head.
So I get the impression that MySQL's storage manager, pluggable storage manager, has been really successful and seen different implementations. But in Postgres, it seems like the AEM API is still hard for people to use because it's kind of tailored to heap AM. Do you have any lessons from MySQL world that you think would improve Postgres' extensibility?
Postgres' extensibility is MySQL's extensibility is interesting in the sense that it's similar to Postgres but very different. They have these structs, and each struct has a handler, and then they invoke the handlers at like various points in the code, which is actually how MySQL implements its storage engines. You just like have a handler that like get data or something, or set data within our storage engine, and then like these handlers are called within the execution engine of MySQL, which actually I think is a pretty intuitive model of storage engine extensibility, which helps with that. Versus I think, Postgres' table access methods are not as intuitive as that. But yeah, I don't know.
Any more questions? If not, then we'll thank Abby for this wonderful presentation. And here's your small gift.